So when they talk about remote sensing, they're really talking about the science of data collection and image interpretation. They're talking about the technology that's used. So we were talking about drones earlier, but satellites as well, all that imagery. And they're also, with image interpretation in particular, they're talking about kind of an art. And it's considered the science and the art of getting information from a distance. So with aerial photography, that's not new. Remote sensed images, they've had that forever, but you can get remote sensing from birds, it's a plane, from balloons, satellite imagery. It's all part of this older study called geomatics, which is the geographic aspect of gathering, storing information using GIS, GPS, and remote sensing devices. So remote sensing is really useful because you don't have to be there, and the drones are another great example. I can be in one place and automate surveillance from a satellite that just covers that area on a repeated basis. It can cover larger areas, and it can go over and cover areas that we're not supposed to be covering. I saw did anybody see The Bridges of Spies, that movie that was just out? Talking about the beginning of the Cold War and the wall between East and West Berlin and the whole Gary Powers spy plane debacle. So they were, we've been collecting aerial photos forever. And so some of the first remote sensing was done during the Civil War. And you can see taking, they would fight on either side of hedgerows or of tree lines. And so one side would get in the balloon and go up above the tree line to be able to kind of see what's on the other side. And so some of our first remote sensing was pretty basic. And then the first flying camera was a pigeon who was outfitted with a little camera. And I expect it to salute, right, any minute now. It's very cute. So that was used in Germany in the 1900s. And then in World War I, we actually had cameras that were mounted on the side of the plane, but the camera operator would have to kind of lean out over the edge and work the camera to get aerial photographs that way. In World War II, we really improved our methods. There was a new film that would do color film. We had the development of infrared film. And the film could go into water depth, which was really important for looking for mines and for submarines. But the cool thing about the near infrared is it would detect troops that were camouflaged, because with vegetation gives off a bright green color, a bright red color with near infrared film. But if you have a tank that has camouflage color over it, it's not going to give off a bright red. It's going to look, gray or brown. So they were able to identify tanks and other equipment that had been painted because they weren't actually giving off that same signal. And this was also a really important rise of women during World War II, because men were out in the actual fighting, and so they used a lot of women to do aerial interpretation, some of the first kind of organized methods of that. And there was a book written about spies in the sky. I never have looked at that. And then in '62, we had the Cold War, which is how we identified missiles in Cuba. We were able to identify just the pattern on the ground that said, wait a minute, this looks like a missile launch site, and able to maybe, almost start a war or almost stop a war. I'm not sure how all that went, but anyway, we ended up being pretty good. In '70, GIS was included with remote sensing, and so now we can bring images in and organize them, analyze them, display them. And some of that was used in the first programs looking at the deforestation of the Amazon basin. So back in '70, we've been doing this for a long time. And So one of the things, like with air photos, you're really just looking at an image on the ground. They're not generalized. You've got that overhead perspective, but things aren't always easy to see. So there's a lot of aspects of an image that you can systematically use to help do some interpretation. Anybody done air photo and you probably have done it and don't even know. Now that we're, oh man, that's not easy to see. Now that we're kind of in the age of Google Earth, a lot of people kind of look at those aerial images and are doing some of this but don't even know they're doing it. So one thing is color is really helpful, right? So if you have color, I can see the difference between trees and fields and water. That really helps me understand land use. Sometimes you don't have color images, especially if you're in Google Earth and we're looking at those older images. Those may be black and white. And so the tone of the image is really helpful. And so that kind of gives you that reflection. So that water will usually have a very high reflectance. So you may have two flat-looking surfaces, but one is highly reflective. That's probably water, and the other might be a field. So being able to look at that and kind of understand those shades of gray. Texture, you can really see texture on an air photo, and we'll look at some images of that. So sometimes things that look bumpy or coarse or irregular can be vegetation or buildings. Gives you a lot of information that way. Shape is critical. Typically, straight lines are human created. So if you see curvy, wavy lines, those may be natural breaks in the landscape. Straight lines, right angles, those are usually always something that has been created by people. Patterns. Again, irregular patterns tend to be more natural. Very regular gridded patterns are human. Size, you can get a lot of information about size by trying to find one thing on an air photo that you recognize and then kind of comparing that out to other things. Or shadow. Shadow will give you a lot of information about the size. And then site is kind of the location where it is in respect to other things. And then just that your own experience is really critical. And having looked at images or having flown, and you kind of begin to recognize what things are. So if we look at shape, you can really see the difference here between that township and range, regular gridded pattern on the right, and the real irregular meandering streams, horseshoe cutoffs, and oxbow lakes on the left. So you really get a sense of human landscape as opposed to a natural landscape. If you're looking for cities, you're the one on the left, you probably would need to zoom in a little more and see if you see a grid in there, but probably would be able to move on. Pattern is looking at kind of that arrangement of things, and I don't know that this is actually the best example of pattern. I'm going to go back to this. But you can kind of see I have some light stuff here, and I have a kind of bumpy stuff here, and there's spaces on either side. So there's some kind of division, and as it turns out, the stuff in the southeast corner is forest. You've got some tree lines in between. When we were looking on Google Earth at the meets and bounds, you were able to see that pattern of hedgerows and land, just based on kind of that repeatability. Shadows give you information about height. So when you look at this building, because the plane taking the image was at an angle, you can really see the shadow reflected by this building. So you may not know exactly how high that is, but you know it's hella higher than these other things beside it, right? Hella higher, isn't that a technical term, right? Texture, again, when I'm looking at texture, here's flat water. You can see it's a little lighter in tone, maybe reflective. very smooth looking, which I can identify as roads because they're pretty straight. And then you've got this bumpy hillside that just shows you vegetation or crops. And then site and association. So here is water, and I've got some straight lines. I've got a big dock. I've got ships coming in. And so you can begin to think about, okay, what would be, in a shipping or dock area. So there might be railroad, very regular patterns of rails. And if you could zoom in closer, you would be able to see those. So it's really looking at all of those different aspects kind of systematically to interpret what you're looking at. And it's much easier with color, but there's still a lot of things in black and white that would illuminate better than a color image. So that's kind of the first part, just looking at those different aspects. And I will ask you to talk about several aspects of photo interpretation, that you would look at and why they would help you identify what's on the ground. There's some very cool ways to actually, I'm not there yet. Never mind. I'm going to be there in a minute. So air photos are taken at different altitudes. So here is a low altitude image taken at about 1,500 feet above the surface. It gives you a lot of detail. Anybody have any idea where this is? Where? No? Black and orange. Does that help? Yeah, it's OSU. It's out there at their front commons. And I'm pretty sure it's spring because those little things are people laying on, it's toward the end of the term. You can see the built, right? These pathways. You can see the trees. I can tell it's probably spring because there's not a lot of foliage on those trees. Could be fall. If it were color, that would help. So I can get a lot of detail from that. A mid-level, most of the topographic maps were created from mid-level aerial photos. So people took photographs and then they would put overlays of acetate over these photographs and draw the original topographic maps and then create maps from that. Now we can do all of that digitally. Not as much detail, but I can definitely see that pattern and I can see texture looking at an image like this, right? So the grid patterns, you can kind of tell where the housing is more dense, where there's bigger lots. I can get a sense of the center of a town or the edge of a town. And then a high altitude, of course, covers more area. And again, I can see a lot about pattern, natural features, irregular features. And that is also Corvallis, I believe. I think that's the stadium, Research Stadium, and then there is the highway. Yeah. So if we look at this image, what generally can you tell about this image? Can anybody identify anything on here? Okay, so how did you identify the river? Is it here? Oh yeah, that's a river. Okay. This might also be a river. Can you see how much reflectance that is? Yeah, and then there's bridges. Good. How did you identify the bridges? But what told you it was a bridge, Ed? Yeah. It's linear, right? It's kind of unnatural looking. It's a linear feature going across. Yeah. Cool. Can you tell anything about what kind of a landscape? Is this farm? Is this... Oh, it's an older city, and it's a lowland. Why do you say older city? Yeah. It's not a regular grid, right? So pretty interesting. And why did you say lowlands, Ed? I don't see much. Yeah, I don't see anything that's like shadowy hills other than, look right here. There's a little bit, so there's something here, maybe a hillside down at that lower corner. How about heights? Did anybody see any clues about where the tallest buildings are in this place? You might have to get closer. Brett? Yeah, right here. There's a huge shadow there. And then I see some other kind of shadows off to the edge. So you can get a lot of information about just a black and white photo. Here's another one, very different landscape. Yeah, Colin, you're right. So I see lots of vegetation, so you get the texture, you get the linear pattern of roads, reflectance of rooftops, right? So you can really get a lot of information just looking at these elements. Here's another one. So I'm seeing texture here that gives me information and pattern. It does. This looks like a pretty big road. It could be. Yeah, I don't remember where I got this one. But I see kind of meets and bounds landscape, right? It's pretty irregular division. I've got some texture up here, and down in here I've got, look at that field that's kind of lined. You can see that bumpy texture. So this field is got some division. It looks like it's probably either growing different kinds of crops or in different stages of being plowed or grown because of the different colors. I don't know. So there's lots of details here. So when you have an aerial photo, they are typically, you have a mark on the photo called the fiducial mark, and fiducial just means, in banking, I think it means, a mark of value or somebody look that word up. It's gone. When you know it's real, when you know it's accurate. Right. Okay. So you trust that this is accurate, right? So when you get somebody who's a fiduciary in banking, you can kind of trust what they're doing. So there's marks on an aerial photo called a fiduciary mark. And so let's say you have a camera down out of the belly of a plane, and the camera, the image is going to be the most accurate and undistorted directly below the camera, right? So if you think about the world is curved, right below the camera is going to be less distorted than on the edges of my aerial photo. So where the camera is called the principal point. And so the principal point is right in the middle usually of the air photo, and it's where these two registration marks cross and come together. So that's called the principal point, or the PP or the P. You'll see it on different images. And I was talking with a student who's doing this online, and he works for the Forest Service, and they are still doing a lot of their planning based on black and white air photos with stereoscopes, lining up the fiduciary points and being able to determine how much area. I said I would love to get some of those photos, but anyway. So it's that same idea that when I have, because these are not projected, the center of my image is the most accurate, and away from this center is the less accurate. So I have a dilemma here. Did I do that? Click to add text. I don't want to click to add text. Thank you. Was that always there? Okay, that's because I'm trying to do this. Delete that. There we go. So I've got an air photo, and I don't know any distance. I can't do any linear distance on here because I don't have a scale, right? So there are ways to determine the scale of an image based on some information about the air photo that should be in the metadata. And the metadata is just data about any kind of data or image that you have. So on an air photo, I should have my fiduciary marks and my principal point, and I need to know how far above the earth the camera was when it took that picture. And if I have that information, I may be able to determine the scale. And I also need to know the length of the camera focal point. So where did it focus on that fiduciary point? So here's a cute little formula. So if I know the camera focal length, which is the f, and I know the height above the surface, then I can figure out the scale of that image. Okay, and so the formula is h divided by, so the height divided by the focal length equals the representative fraction. All right, and if I know the representative fraction, then I can measure things and figure out how far things are apart from each other. So here is kind of how that would work. Sometimes a plane isn't flying just at sea level, right? So if the ground elevation is 1,000 foot above sea level and the height of the plane is 4,500 feet, then I need to be able to subtract those two to figure out actually how far that plane is above the ground that it's over. Does that make sense? Maybe, maybe not. Okay, so if I'm flying above sea level, right, and the ground is at 0 feet above sea level and the plane is at 4,000 feet, then my height is 4,000 feet. But if I'm flying above a hillside that's 1,000 feet and my plane's at 4,000 feet, then my height is really only 3,000 feet. Okay? So in order to figure this out, I need to know how high the plane is and then also the ground elevation to be able to make that calculation. So let's say the plane's at 4,500 feet above sea level. The ground elevation is 1,000 feet. So that my h is actually 3,500. Okay? And my focal length is 12 inches. The focal length of my camera. All right? So one thing I have to do is I have to make sure everything's in the same units, because I want to be able to divide the elevation by the focal length. So I have feet in my elevation and inches in my focal length. So I just changed my inches to feet, and my representative fraction was 1 to 3,500. Okay? If my focal length had been only a 6-inch camera, then I would have divided it by 1/2 foot, and then my representative fraction would have been 1 to 7,000 feet. Okay? So now that I know that, it's pretty cool. I can figure out what my elevation is.
6 inches wouldn't be like 0.6.
6 inches is 1/2 foot, so I can divide it by 0.5, right? Yeah, and I could have converted this to inches, but that's way bigger division numbers for me than than the other way around. Yeah. Okay, so here is one for you to play with. So what if the plane is 1,500 feet above the surface and the focal length is 1/2 foot? What would your representative fraction be? So just kind of have to do the math here. 1,500 divided by 0.5. Okay. Everybody get 1 to 12,000? I hope not, because that wouldn't be right. Uh-huh. 0.5, 1/2 foot. Oh, wait. Am I wrong? Yes, it was an inches. Oh, I'm wrong. Okay. Yeah. Well, 6 inches is 1/2 foot, right? So we did by 0.5. So what did anybody get? Okay, well let's just go back up here for a minute, okay? So 1/2 foot is 0.5 feet, right? Okay, so if I take whatever that was, divide it by 0.5, let's see if we got that back, right? Let's just look.
1,500 divided by 0.5 is 3,000.
Yep. So I'm going to take 1,500 divided by 0.5. It's 3,000, right?
Or 1,500, but you have to compensate for the 100 yards, which is actually...
Not yet. We're not there. That was the next one. Yeah. Okay. So if you take your 1,500 feet and divide it by 0.5 feet, you get 1 to 3,000. So your RF is 1 to 3,000. Okay. Now, Billy, you're right. Now I've got the ground elevation is 100 yards. So 100 yards is how many feet? Okay, so now I've got to take that 1,500 minus 300 first. And then I'm going to divide that. Right, 1 to 2,400. Okay? So the second problem says, if the plane is at 1,500 feet, but the ground elevation was 100 yards, right? So 1,500 feet minus 300 feet.
Why 300 feet instead of 100?
Because that's yards. So I've got to convert that to feet.
Okay,
Yeah, tricked you. All right, so I've got 1,200 feet is my actual elevation above the surface, right? Now I'm going to take that 1,200 feet and divide that by 0.5, which, Desiree, if you just multiplied it by 2, which was your initial idea, it would have done the same thing. Yeah, right, because you can invert and multiply instead of dividing by fractions. Either way would work. Okay, so, and you would write that as 1, 2, right? Oops. Yeah. Oh, no, don't do it. Don't do it. Okay. Let me do a dummy thing in here. I wonder if it will let me do that. It thinks everything is a formula. Now if I do 1, 2, 24, let's see if that will work. Yay. Okay, so that would be how you would write it without the silly asterisk. Okay? All right. So that will be on the video. You can watch that over and over ad nauseum. Okay. So there's 2 different ways to actually figure out the height of an image. One of them we're not going to do because it involves way too much information. There's one called the shadow method. Has anybody ever done that, where you have to use trigonometry and what is the angle of the sun at the time of the day that you took? And all of that should be in your metadata with your photo. Okay? So that is probably the most accurate method of doing that. You figure out the length of the shadow, you figure out the angle of the sun, and it's, again, I think it's just using the Pythagorean theorem and figuring out the height of the tree. But there is another way that we're going to do that, which is pretty accurate, called the displacement method. Okay? So the displacement method depends, again, on what's called the principal point. You have to have that true vertical point on your image, and you have to know the altitude of the photo, of the plane. Okay, so you need both of those too. And then if you know that, you can do what's called a displacement of the shadow or of the bottom of the image. Okay, so it might be best just to kind of show you what that looks like, and the lab will get you working with that and practicing that. And oh shoot, this is a demo, but anyway, I'm going to try to do it. I can't do demos and run the video. But anyway, okay. So there's these variables that you need. You need the height of the object. Okay? That's what I'm looking for. I'm looking for what is the height of the Washington Monument here, right? I don't know what that is. So I need to know the height of the plane. So I've got that. It's 1,500 feet. And I need to know what's called the displacement. Let me go back here. Is the length of the displaced image. So from the bottom of the Washington Monument. Are you going to let me move this, or is everything going to move? Crap. Okay. So if I can get in with my ruler and measure the base of the Washington Monument to the tip of the Washington Monument, that's going to give me my displaced value. So when I measured this D was 1.8 inches. Okay, so this is where I use my decimal ruler. And then I'm going to see if I can line that back up. No. Okay. Then my next value is this R value, which is the distance from the principal point to the top of the object. So it's going to be from this principal point to the top of the Washington Monument. So now what I have is a ratio that I can figure out how long the Washington Monument is.
How did you come up with the principal point?
That's on the photo. If that's not on the photo and you don't have your fiduciary marks, you can't do it. Okay? So as long as you've got your principal point showing up on your image, and you're going to measure the displacement of the real object, and then you're going to measure the distance, then you've got this great little formula, and you have to have the distance and the R have to be in the same units, but the height does not. Okay? So you can ignore all the units in this one, because these two units cancel each other out, basically. So what you're going to do is divide the length of the object by the length from the principal point to the top of the object, and then multiply that by the height. And you're going to get the height of the Washington Monument. So, does anybody want to try that? How many? Okay. 562.5. Somebody want to Google Washington Monument height? It would be easier. It would be easier. So, pretty close. Pretty close. That's not bad figuring, when you figure how small this image is and how coarse our measurements are. So you guys are going to be amazed at how well you can measure the height of the Hancock Tower on an air photo, which is only about 2 inches long. You'll get really close. You'll get really close. So in the lab, you're going to measure. You're going to figure out the scale of an aerial photo based on the height and the focal length of the camera. You're going to figure out the height of some towers based on this displacement method. And then you're going to use a method to figure out the representative fraction on an air photo that you don't have any metadata. You don't have a principal point. You don't have anything to use. And we did a little bit of this when we played with the scale lab that was so badly developed a few weeks ago. So one of the things you can do is use a topographic map where you know the scale, and then you can compare the distance between the two maps, measure something, and then create a ratio. So basically, I know that the image on the right is from a topographic map, and the scale is 1 to 24,000. So that's considered the map scale. And so I found a really easy section of road to measure, and I measured from here to here on that topographic map, and that's called the map distance. So if I multiply the map distance by the map scale, and then divide that by that measuring the same distance on the air photo, I'm going to be able to figure out what the scale is of the air photo. Okay? So I found those two places, and I measured from, I think that might have moved a little bit, but maybe not. So I measured from that intersection to that intersection, which is the same location, and then I was able to figure out what the representative fraction was for that air photo. So maybe. So for the lab, you have You don't even need a computer to do this today. I'm going to print all of these off in color for you because it's really helpful to have this in color. So the first thing you're going to do is determine the representative fraction for this air photo image, and I gave you the formulas are up here, so that will help, I hope. The next thing is to figure out the height of these two towers, Tower A and Tower B, or not. Come on. And so you'll measure this one. You can see the bottom of Tower A and the top of Tower A. And Tower B I can't show you in this because it's, oh, there it is. The bottom of Tower B and the top of Tower B. And the formulas are here. So that gives you the displacement formula for that. 2 and 4, because apparently I did not like the number 3 that day. Question 2 and 4, you're going to figure out the focal length or the representative fraction based on the height and the focal length. And then that red line is the bottom of the Hancock Tower to the top of the Hancock Tower. Let me see if I can show you where. Oh, come on. Come on, you can do it. You can do it. Maybe you can't do it. Let's see. There it is. So I've got the line for you. So there's the bottom of the Hancock Tower to the top of the Hancock Tower. So based on that, and the principal point is in here somewhere. Yeah, there's the principal point. So there's the fiduciary mark. So there's the principal point. So by using displacement, you're going to be able to figure out how tall the Hancock Tower is. And then you're going to figure out something else. I don't remember. Oh, you're going to figure out the representative fraction for that air photo. And you're going to use that based on this topographic map. And then I want you to talk about this amazing air photo, which is a classic air photo. And talk about what you see and what could be happening here. It's a Second World War air photo. So this typically has gone very well. So what I'm going to do is print this out in color for you.